Electrochemistry. We all have a pretty good idea of what chemistry is by now. Electrochemistry is simply the study of chemistry in terms of transformation of energy from chemical to electrical energy. And for most people, think batteries, but not just batteries, because battery is a spontaneous reaction that gives you a voltage that can do work. But if you want to run the reaction in reverse, all you have to do is apply a reverse voltage that's greater than the spontaneous voltage, and you can get the reaction to go backwards. That's what happens under the hood of your car every time you turn on your engine. Right? It takes energy from your battery to start your engine. So you put that energy back. Once the engine is running, you take chemical energy from your engine, you run the alternator, and it runs the reaction in your battery backwards. We call that recharging. Okay. All right. So here's some terms that we need to either introduce or review. I can't remember. We've done electrochemistry. I just did that. Oxidation reduction reactions. Remember what those are? No. In order for an oxidation reduction reaction to take place, electrons must be transferred from one atom to another. That's what's meant by oxidation reduction. Let's see. In fact, I have a slide, I believe. Well, this is it. Oxidation. Anytime electrons are lost from any atom, we say that it's oxidized, and oxidation has taken place. That's why this is oxidation is loss. Right? That's the oil part. The rig part is reduction, is gain. So anything that gains an electron is reduced. There we go. There's your handy dandy acronym. If you ever forget, just remember oil rig. I'm going to talk about the reducing agent, oxidizing agent, just a minute. Well, I guess I better talk about it now. All right, let's how about hydrogen and oxygen makes water. Okay, so let's see, I got to balance this equation. There we go. Okay. Well, actually, now that I think about it, we need the rules first before I can do this. Okay, so the rules are, number one, in terms of oxidation state, we haven't defined that yet. Oxidation state. It's kind of like a charge, but not always a charge. An oxidation state is a method of bookkeeping, so we can track the electron movement. We say the oxidation state of an element in its most stable form at room temperature and pressure is 0. So the oxidation state of this hydrogen, since hydrogen is a diatomic element at room temperature, 1 atmosphere pressure, its oxidation state is 0. Right. Remember, when we write a symbol, the upper right-hand corner is where you put the charge. We're going to borrow that. Instead of putting a charge, we're going to call it oxidation state. It's only a charge if you have an ion. That oxidation state is 0. This oxidation state is 0. Right? Because it's a pure element under 1 atmosphere pressure and room temperature. Okay. If we have any ions, then their oxidation state is the charge. An element that is an ion, like Let's say we're putting sodium chloride in water. We know how to do that now. That oxidation state is +1. This oxidation state is -1. Actually, this is an ionic solid, right? So it's a combination of ions. It's still oxidation state 1 and -1. All right. If oxygen is in a covalent compound, not an ionic compound, but a covalent compound, we assign an oxidation state of -2. So this is a covalent compound. Its oxidation state will be -2. The only time that's different is if oxygen is in a peroxide. And there are several examples there on the slide. A peroxide is 2 oxygens hooked together and then whatever else. So the top one is showing you that if you have a peroxide ion, it's a 2- charge. That means each one of these oxygens has to be a 1- charge. Okay, this is the only time that oxygen in a covalent compound doesn't have a -2 oxidation state. If it's in a peroxide, it's a -1 oxidation state. Right? Rule number 4. Hydrogen. If hydrogen is in a covalent compound, it will have an oxidation state of +1. So this oxidation state for hydrogen is +1. We'll do a balancing act. 2 times the +1 is +2. It balances at -2. Right. That's another rule that's coming up. However, if hydrogen is bound to a metal, it's not a covalent compound, it's an ionic compound, then hydrogen has to assume a -1 charge, -1 covalent oxidation state. So aluminum trihydride, aluminum is going to be a +3. And hydrogen is going to be a -1. Fluorine. Anytime fluorine is in a compound, doesn't matter what it is, covalent, ionic, in between, it's always a -1. Okay. Now, while we're on that topic, what does that say about the other halogens? What it says is it depends. If you're stuck and you have to calculate the oxidation states for other elements in a compound, and a halogen's in there with them, we assume that it's a -1, just so that we don't get stuck. And we'll do some examples with it. Some of the oxidation states for a neutral compound must be 0. So the sum of the oxidation states for water, 0. 2 times +1 is +2, -2, 0. The sum of the oxidation states for a polyatomic ion have to equal the charge on the ion. Right? So let's see. How about the hydroxyl ion? Right? Hydrogen would be a +1. Oxygen would be -2. -2 and +1 is -1. There you go. It all adds up. And you can do that for any of the polyatomic ions. We'll do a few for examples. Alkaline metals are always +1. Alkaline earths are always +2. Just like the charge when we were writing compounds, nomenclature and writing compounds. We assume that alkaline metals are 1, alkaline earths are +2, aluminum is +3. I didn't put it there, but it is. When chlorine or nitrogen are present with none of the above, Right, we have to make a decision. So if we have carbon, nitrogen, what do? Because the others have to be calculated. These are given. We'd have to calculate carbon. Well, we weren't given a rule for nitrogen. So in a situation like this, we go to the more electronegative element and assign it a value. So remember when we were writing compounds, we assumed that these were all -1, ionic compounds in particular. These are all -2. These are all -3. So we give nitrogen a -3. It has to be a -1 total. So that means carbon has to be a +2. +2 and a -3 is -1 for the cyanide ion. This one, phosphorus pentachloride. If we don't assume that chloride is -1, we're stuck. So we say this one's -1, that's -5 total. Phosphorus has to be a +5 because it's neutral. All right, so now we have some other examples. I'm gonna leave that one up there because I want to use it in a minute. So how about potassium dichromate? We're given values for the alkali metals, right? +1. We're given oxygen, -2. So potassium contributes a +2 to the total. Oxygen contributes a -14 to the total, right? 7 times -2. So what do we have to balance with those chromiums? Well, add these together, -12, right? So, okay. So chromium, in order to balance and become neutral, has to be +12 total. Plus, right? Because it has to come out to 0. We've got to add that to be 0. Remember? Okay. If this is +12 total, and we get 2 of them, how much for each one? +6. And you can check it for yourself. Just take those values. Do the math. +2, +12, -14 equals 0. Okay. How about carbonate ion? This total has to come out to -2. This is a polyatomic ion, right? So oxygen is -2 times 3 is -6 total, right? So what would carbon have to be to give you a -2? +4. +4 and a -6 is -2. Now we just did that in our heads. But if you're getting in a hurry on a test or something, and you need a method that's more reliable, you've got a -6 here from that carbon. We know we have to balance part of those charges. So let's say we hold out 2 of those minuses for that one. That means you really only have to balance a -4 with that carbon. So a +4 will balance. We'll balance these and leave 2 minuses left over. That's the way I look at it. I hold out 2 of those negatives for the charge, and then I balance the rest. Let's see, I've got some animation in here. Yeah, there we go. And there. Manganese dioxide. The rules say that this one's -2. So that's a -4 total. And we've got a neutral compound. So this manganese has to be a +4. PCl5, we did that one already. So I'll just throw that one up on the board. How about SF4? We were given a rule for fluorine, weren't we? -1. So that means -4 for all those fluorines has to be balanced by 1 sulfur at +4. We have to know how to do these things. Otherwise, we can't track the electron movement in a reaction. Okay? That's why we're hammering this idea first. Able to calculate, to memorize the given values and calculate the others. All right. Let's see. Yeah. Before we take off with that slide, let's finish this equation off here. Okay. We have to decide which one lost and which one gained electrons. Right? Oxidation is loss. So which one lost? Well, I like to draw tie lines. We'll go from this hydrogen to that hydrogen. Okay. In that process, how many electrons were lost or gained for each hydrogen? We went from a 0 to a +1. So we had to lose 1 electron, right? For each hydrogen. So that's our loss. Lost 1 electron per hydrogen, but we got 2 of them, right? 2. Actually got 4 hydrogens. Right? Coefficient times the subscript. So times 4 equals 4 electrons lost in that process. Okay, let's do the other one. Well, the other rule I haven't mentioned yet is you can't have an oxidation without a reduction. They're joined at the hip. If you have an oxidation, you have to have a reduction. So if this is the oxidation, then this has to be the reduction. Gain, how many electrons per oxygen? From 0 to -2. Gain 2 electrons per oxygen. Well, we got 2 oxygen, right? 2 there, 2 there. Times 2 equals 4 electrons gain. Notice that the number of electrons lost has to equal the number of electrons gained. Otherwise, you build up static charge. And we don't do that in chemistry. We leave that to the physicists. And they're Van de Graaff generators. They're high voltage things. When I was a kid, I lived in Oak Ridge, Tennessee, which was one of the centers for research in nuclear physics. So our public schools were the best in the country because we had the highest concentration of PhD chemists and physicists and engineers in that city. So they demanded good schools for their kids. So I was lucky. My dad wasn't any of those. We were there for other reasons. But I got to benefit from schools. And one of the things we did was we took field trips to labs and to demonstrations of various types. We went to this one where all these little kids, the grade school kids sitting out there, and they had this device sitting up on the platform. And it was a tower with a big silver ball on top, the Van de Graaff generator, which would produce electric charge. So the speaker found the prettiest little girl with long blonde hair, brought her up to the stage, said, "Now you grab hold of that thing, that big round silver thing, and don't let go." Right? Turned on the generator. As the charge built up, charges tend to leak from points. So the charges moved through her body, through her hair, out to the tips of the hair, and all those electric charges repel one another. So her hair stood up like this. And then we all had a good laugh. He turned the generator off, let it discharge, and her hair went down like that. Then she turned loose. But we don't do that. We don't do static charge in chemistry. Everything has to balance. Okay. So, this is oxidized, right? Yeah, oxidation is lost. This has been oxidized. This has been reduced. And then two other terms. When something is oxidized, it loses those electrons to something else and causes reduction. So the electrons lost here cause the reduction of oxygen. That makes this the reducing agent. It's the cause of reduction for oxygen. And conversely, this one is reduced. It gained electrons and it caused the oxidation of hydrogen. So this one is the oxidizing agent. Okay. For terminology. All right. Now we can get on to how do we deal with various equations. First thing we're going to do is take this balanced equation, hydrogen ions plus manganate ion plus iron 2 plus ion yields manganese 2 plus and iron 3 plus in water. First thing you'll notice is if you try to add up the charges, they don't add up. The reason they don't add up is because we have removed the spectator ions from the equation, those that don't matter. They're just there for balance. So these are the ions, molecules, and atoms that are essential for the equation. That's the first thing. The second thing is given. This equation is balanced, just so that we can introduce the concept of half reactions. So if we write the whole equation out in its balanced form, we're going to show you how to get to this balanced form from an unbalanced one in a minute. Manganate ion and ions. Iron plus, actually it's probably in equilibrium. Manganese 2 plus and iron plus in water. 4, 5, 8. Okay. So in order to assess where the reduction is occurring and where the oxidation is occurring, we need to know the oxidation states for all the elements. That's easy. That's a +1. Just chart. That's a +2. That's a +3. That's a +2. Those are all given because they're individual ions, atoms that are ionized. We need to calculate this one. Okay. So oxygen is -2. 4 times -2 is -8. We're going to hold one of those negatives out for that charge. Okay. That means we only have to balance -7. So this one is a +7. Okay. Water, we did water before. This is -2 and this is +1. Okay, now let's see. Where did the reductions and the oxidation take place? Let's see. Hydrogen went from a +1 to a +1. It's a wash. Nothing happened there. Manganese went from a +7 to a +2. Aha. So what happened here? If you go from a +7 to a +2, you have to introduce some negative charges, right? 5 negative charges will bring that from a +7 to a +2. So it gained 5 electrons. 5 electrons per manganese. But since we've only got 1 manganese, that's 5 electrons gained total for this balanced equation. So oxidation then would have to be, nothing happened to the oxygens. The oxygen is still -2, -2. We went from this one, a +2 to a +3. So it had to lose an electron, didn't it? Had to lose an electron. We had a loss of 1 electron per iron times 5 irons equals 5 electrons lost. So we balanced our electrons. This one was reduced, this one was oxidized. Now to the concept of half reactions. We can break this apart and write it in terms of the reaction that is occurring for the reduction and the reaction that's occurring for the oxidation. Okay. The reduction step is going to include hydrogen, oxygen on this side, the manganese, and manganese, hydrogen, and oxygen on that side. So we have to keep those all together. So this reduction step is going to be 8 hydrogens plus 1 manganese. And that is equal to 1 manganese 2 plus and 4 water. That's the reduction step. So what's left over? Well, what's left over is we have 5 iron 2 plus in equilibrium with 5 iron 3 plus. Now what's missing? Electrons, right? So if we gained electrons, they go on this side. Right? They go here into there and they disappear. They're contained over here. Okay. So we had to add 5 electrons here. That means we had to lose 5 electrons over here. They come out as products. Those are the half reactions for this balanced equation. Okay. These are the instructions for taking an unbalanced equation and balancing them. So we go from here to there rather than from here to here. But the reaction as given is going to be unbalanced. So we need a methodology for balancing equations using the half reaction method. Now we learned in first semester how to balance equations with my budget method. Okay. That works for a great many reactions. There's some that are really ornery. They don't want to be balanced. And those are very often redox equations. So this method comes in really handy to balance redox equations. And there are some occasions where you only partially balance it with redox, and then you finish it off with a budget. But we're going to focus on half reaction method for balancing an oxidation reduction equation. First method we're going to learn is in acidic solutions. And it'll become obvious why in just a minute. Okay, so these are the instructions, and I'm going to leave them up there long enough to get recorded, and then we're actually going to do one. And there's a flow chart if you like flow charts. All right. So let's balance this equation. Dichromate ion. And again, it probably doesn't charge balance. Right? On the left-hand side, we have a -4. On the right-hand side, we have a +1. Right? So that obviously doesn't balance. And we shouldn't expect it to balance now because the equation is unbalanced. But we're missing the spectators. Right? Dichromate, it could be potassium dichromate, it could be sodium dichromate, doesn't matter. Those ions aren't important for this reaction. All right, so we have this dichromate ion. That. And they're all in aqueous solutions, so I'm going to leave that out for so it doesn't take up the whole board. Then we have the sulfite ion. And this is in equilibrium with the chromium 3+ ion and the sulfate. All right. So the first thing we have to do is oxidation states. So we tell which way the electrons are moving. Chromium here. We did chromium already, but look, that was with a complete compound. This is with a polyatomic ion, and we should get the same answer. So we have -2 for the oxygen times 7 is -14. But we're going to hold out 2 of those minuses for that charge. That means we only have to balance 12, right? Let's see, did I do that right? -2 times 7 minus 1. Well, yeah, okay. So this one has to be +12 total, which means each one is +6. Okay. I don't know if you've heard, well, not recently. There used to be a big stink about oxidation states for chromium and which one is more polluting, which one is more toxic. The chromium 6+ ion is not very toxic. The chromium 3+ ion is. So they would say hexavalent versus trivalent. The trivalent chromium is the nasty one. But the EPA and OSHA still said we can't use it. So we used to make up a solution called chromic acid. We use sulfuric acid and potassium dichromate and mix up a nice strong solution. You can put your glassware in that, it would clean it out in no time. It's the best stuff ever. Can't use it. How's the chromium? Now, just in their defense, chromium 6+ in the environment can be reduced to chromium 3+ by microorganisms. So that's probably where they're going with that one. Okay, back to the problem. Okay, we got those values now. Let's go to the next one. So -2 for oxygen means a -6 total. We got to hold 2 of those out for that charge. So we only have to balance -4. So this is a +4. Okay. This one is already given, 3+ for that chromium. This sulfate, -2 times 4 is -8, hold 2 of them out. -6 we need to balance, so that's a +6. Now we got all our oxidation states. Which one is the oxidation step? Which one is the reduction step? We got to put everybody in their cubby holes. We went from a +6 to a +3. That means we had to gain electrons, correct? Yeah. So this one's going to be reduction. Cr2O7, 2 minus total. I'm going to put this in here just since we went to all that trouble. And it's going to give us, going from a +6 to a +3, it's going to give us this. So that's everything from that unbalanced equation for the reduction step. The oxidation step has to be the other one. So SO3 2 minus with a +4 here goes to I'll put it on SO4 2 minus with a +6. So yeah, we lost 2 electrons per sulfur. Okay, the next thing you do is you balance elements that are not hydrogen or oxygen. We're going to do those later. So we got 1 sulfur here and 1 sulfur there. It's already balanced. We got 2 chromiums here. We need 2 chromiums here. Okay. Now we balance the oxygens. And we balance oxygens with water molecules. So we have 3 oxygens on this side and 4 on that side. How did we get 4 oxygens? we need another oxygen on this side, don't we? There's your oxygen. 1, 4. 4 oxygens. Okay. But we've added hydrogens. So now we have to balance the hydrogens on the other side. We do that with hydrogen ions, protons. So we got 2 hydrogens here. We need 2 hydrogens there. Okay. This one, we've got 7 oxygens on this side. We need 7 oxygens on this. So we use water molecules. Now we've introduced 14 hydrogens. So we balance the 14 hydrogens over here with protons. Okay. That's why we're saying this is acidic solution. We've added all these hydrogen ions. This solution is acidic. Okay. Now we need to put the electrons in. How many electrons went from here to here? This is the oxidation step. We lost 2 electrons per sulfur, and we've only got 1 sulfur. So these 2 electrons, this 2 minus and a +6 is a +4. Okay. Reduction step, we need to add electrons on this side. So how many? Well, we've got 2 times 6 plus. 2 times 6 plus is a +12. Well, let's do chromiums. Let's just do individual chromiums first. 6 plus and 3 plus. We have to gain 3 electrons per chromium, right? But there are 2 chromiums. So we have to gain 6 electrons, correct? Okay. There we go. Now our half reactions are balanced. We can't put them back together until we've got the same number of electrons in the oxidation step as in the reduction step. Remember, if you get electrons moving from one place to another, they've got to show up same amounts for the oxidation and reduction. So we got 2 electrons there, we've got 6 here. How do we get 6 electrons there? Multiply by 3. This equation is already balanced. So the only way we can change that is to apply the same factor to every element in the equation. Okay. So now that 3 goes here, here. 3 times 2 is 6. So now we got the right number of electrons. 3 times 2 is 6. And 3. Okay, we use that up. Now we can put them back together. So we need a summation line. Let's add these together now. Let's try to put them in the same order we have up here. So 1 dichromate ion. And then we had 3 SO3, 2 minus. Okay. That one, that one. Now we have 3 water. And we have 14 hydrogens. And we have 6 electrons. Now we'll bring these down. Chromium first. 2Cr plus 1. And then sulfate plus SO4 2 minus. That's done. Then we had let's put them in the same order. Waters. Let's put 7 waters here. And then hydrogens. 6 hydrogens. And 6 electrons. So we brought everything down. We got check marks on all of these. Didn't check these. They're down here. I didn't check that one. Okay. So now what do you do? Well, if you've got reactants on one side and some of them are products on the other side, we want to cancel them out. We don't want to have hydrogen. Let's take hydrogen ions, 14 on this side and 6 on that side. So that means cancel those out, and we're left with 8 hydrogen ions on that side. Let's see. These are good. These are good. Water. We got 7 waters over there. We got 3 over here. So those 3 go out, and we're left with 4. Okay. Electrons. So in the balanced equation, you don't see the electrons. Now, for later calculations, you need to know how many electrons moved. When we get to a little teaser, when we get to the Nernst equation, you need to know how many electrons moved. So even though we cancel them in this balancing, make the mental note of how many moved. 6 moles of electrons moved in this reaction. Okay, so we've got 1 dichromate ion, 3 sulfide ions, 8 hydrogen ions, acidic solution, yield 2 chromium 3 plus 1 sulfate ion, plus 4 water. Now, all this is happening in the same solution, right? So just because these hydrogens are on that side doesn't mean they don't play around over here too. Right? This is all the same mixture. So the whole solution is acidic. We have extra hydrogen ions. All right. So let's see. These slides are supposed to do exactly what I did on the board. And we end up with final balanced equation. All right. While we're here, suppose you were told that the solution is not acidic, but it's basic. Right? How would we do that? Well, we use what I call the fake acid method. You balance it acid first, then you convert it to base. So how do we convert to base? Neutralize the hydrogen ions. So we have 8 hydrogen ions here, right? So we're going to add 8 hydroxyls. That gives you 8 water. But now we have to put 8 hydroxyls on that side. Okay. Now we've got 8 waters over here and 4 over there. So these 4 go away, and we're left with 4 waters. So in basic solution, this would be the dichromate ion, 3 sulfide ions, 4 waters, 2 chromium 3 plus ions, 1 sulfate ion, 8 hydroxides. That's balanced in basic solution. Okay. Now, theoretically, you could balance this equation using this method, go straight to basic solution, but it's really difficult. It takes many more steps. This is really the simplest way. Balance it acid, then convert it to base. Much less chance of problems. Okay, how do we balance this one in acidic solution? I'm going to let the slides do the talking for this one. I thought I'd at least show you one of them in longhand. Now we'll type the rest of them. All right. Right there. All right, bromide ion plus manganate ion yields liquid bromine and manganese 2 plus. So the first thing we do is we have to decide which one is oxidation and which one is reduction. Whoops. Skipped a bunch of steps. I guess I will have to put this one on the board. So since we've got a mix of aqueous and liquid, I better put the states in here. Yeah, let's see, bromine, liquid, and Mn2 plus. Okay. First thing we need is oxidation states. Okay. That one's easy, -1. This one's a 0. It's elemental. And this one's a 2 plus. So the only one we need to calculate is this one. -2 times 4 is -8. Hold one of them out. -7. So that one has to be a +7. Okay. All right, now we can decide which one is oxidation and which one is reduction. We went from bromine as a -1 to a 0. How did it get there? Had to lose an electron, right? Yeah, had to lose 1 electron for each bromine. So that is oxidation. Get the bromine minus yields Br2 with its plus. That means the reduction step has to be the manganate ion. This +7 here, the charge here, and then we get Mn plus. So yeah, that was reduced, went from a +7 to a +2. All right. Then we balance the non-oxygen, non-hydrogen elements. We got 2 bromine atoms over there. We need 2 here. Got 1 manganese here, 1 manganese there. That's good. Now we balance the oxygens. No problem there. We don't have any oxygens. Right? So we just work with this one. We got 4 oxygens here. That means we need 4 oxygens here. But we've added 8 hydrogens. Got to balance the hydrogens.
So you got 8 because there's
2 times 4.
Okay.
Okay, now we can balance the electrons. So we went from a -1 to a 0, means we had to lose 1 electron for every bromine. But we have 2 bromines. So we lost 2 electrons. Here we gained 5 for every manganese. Because we went from a +7 to a +2. 5 electrons. Because there's only 1 manganese. Now we want to balance the electrons. How do you balance 2 prime numbers? A 2 and a 5. No ideas? Cross multiply. Take this 5, go up here. And you take that 2, and you go down here. Now, will that work? Yeah. 5 times 2 is 10 electrons. 2 times 5 is 10 electrons. So the rest, we're just going to crunch some numbers. This is a 10. This is a 5. And this is a 10. This is 2 times 8 is 16. And 2. Use that up. And this is a 10. 2 times 4 is 8. And then we have a 2 here. Okay. Now we can add them together. Why don't we cancel some stuff before we get that far? Bromines, we're not going to cancel those. Hydrogens. Do we have hydrogens on that side? No, only hydrogens over here. Manganese, electrons. We can cancel the electrons. Now we can bring everything down. So let's bring them down in the same order. 10 bromide ions. And then the manganate plus 2 manganate ions. There. There. And then what else do we have? 6 hydrogen ions, 16 hydrogen ions. There. Let's clear that. Now the other side, we start with bromine here, 5 bromine liquid. And then we have 2 Mn2 plus. Okay. And we also have, let's see. Slow, check off. 8 water. So that should be 10 bromides, 16 hydrogens, 2 manganates this side, 5 bromine 2s, 2 manganese 2 plus, and 8 waters. So we got a balanced equation. All righty. I'll give you a little heads up. These half reactions, 1/2 reaction goes in one half cell of a battery. The other reaction goes in the other half cell. Just a teaser. Okay. To balance in basic solution, I use the fake acid method. So you balance it as an acid, then you neutralize the hydrogen ions. So we don't need to go through those steps because they're all the same until you get to the balanced acid equation, and then you just neutralize your hydrogens with hydroxyls. And there's a flow chart if you like flow charts. Okay. Oh, this is a little comment on, suppose you tried to balance the equation straight to the basic form. What if you started by adding hydroxyls first instead of hydrogens? Hydrogen ions. Right? You balance the oxygens with water. Then you balance the hydrogens that you just added on one side with hydroxyls on the other side. Well, if you do that, you've added oxygens again. So now you got to go back and do the oxygens over again. So it's back and forth, who knows how many times to get it straightened out. With the acid method, you're only balancing the hydrogens with hydrogen ions. Right? So it's like the budget method, where we said, okay, what was one of the tricks from the budget method? If you have any straight just elements on one side, hold those for the last. Because any coefficients in front of those is only going to change that. So you don't want to go into an endless loop going backwards and forwards. Same thing here. All right. Where's my arrow? There it is. So if we balance this one in basic solution, we do it in acid solution first. And, well, do it in acid solution first, then neutralize the acid. And you should get that equation. Do I need to do that? That's one for you to try out. Right? Balance it in acid solution first. Okay. So you're going to have manganese in one equation and cyanide in the other equation with oxygens in both of them. So they're both going to require additions of water and balancing with hydrogen ions. Then once you've got the balanced acid equation, then you neutralize the hydrogens with hydroxides. And you should come out with that equation. Okay, now to batteries. Also known as galvanic cells, named after the Italian, I forget his first name, Galvani. This device converts chemical energy into electrical energy. When we have these balanced equations up here, I mentioned that all that stuff is in the same solution, right? So the electrons are being transferred in that solution, right? Well, how do you get energy out of that? There's no way to access those moving electrons because that's where the energy is. So we need to figure a way to make those electrons go into an external loop so that we can access them on their journey. That's where we have one half reaction in one cell, the other half reaction in the other cell. And then we connect them with a wire. So electrons, let's say the electrons are moving this direction. Now we can measure a voltage and we can gain electricity from that chemical reaction because we force the electrons to go external. That's a galvanic cell. The reaction will be spontaneous in one direction. And by convention, the reaction is spontaneous in this direction. Right? The way we write it. But what does that mean? If electrons are being drawn out of here and sent someplace else, this side is oxidized, isn't it? It's losing electrons. So this is the oxidized side, and this is the reduced side. Because the electrons are showing up over here, but they got to go somewhere. So they go into something to reduce it. Okay. Now the reaction, since the electrons are our business, they're moving from here. The reaction, the oxidation occurs right there at the electrode, and the reduction occurs right there at the electrode. It doesn't occur out here. It occurs at the electrode. That's where the electrons are either leaving or arriving. Now, sometimes the electrode is a participant. It's a reactant. Sometimes not. It just depends on the chemistry. But you always have to have some type of conductor here. If that conductor is not participating, and that means it's usually a metal. If it's not participating, then you have to put something in there that will serve as a collector for the electrons or a distributor. And that could be a platinum electrode, right, which is unreactive, usually. Or it could be a graphite electrode. That's what they use in dry cell batteries, right? That center post right there where that nipple is on top. Under there is a carbon rod. It doesn't participate in the reaction. It just collects the electrons. Okay. So here's the possibility. If you have these electrons moving here, one, let's see, what would you call it? A maxim of electricity. If you study electricity in physics, you know that electrons will not move. You can't get a current unless you have a circuit. It's got to be a complete circuit. So this is not complete, right? If those electrons moved over here, we get an unbalanced charge. Right? We set up electrostatic charge and that would work. So you need to complete the circuit. One way is with a salt bridge. So we provide ions that can move between these half cells and keep the charge balanced. The other way is to put a porous disk in between them. Porous disk, there's a concept in batteries called internal resistance. Everything's moving. And if there's a lot of resistance in the battery itself, then you're going to decrease the amount of voltage you can get out of it because it has that resistance built in. If we want to reduce the resistance, then we don't want to use this long tube with lots of ions in the way. So one way to do that is put a porous disc in the middle. What we want to do is allow ions to move, but not for the solutions to mix. So the porous disc, it's very, very, very fine pores. We'll keep those from mixing. That's two ways to complete the circuit. Now with a complete circuit, you can measure and charge. So in the lab, when we build our battery, you can prepare your solution on one side, prepare your solution on the other side. You can hook up your meter to the electrodes. Like you're going to have a meter up here, hook it to your electrodes and stick them in the solution, and nothing happens until you submerge that salt bridge. Or you can put the salt bridge in and just disconnect one of those electrodes. As long as there's no circuit, there's no chemical reaction, and there's no movement of electrons. So if you want to find out the voltage at the very instant you start the reaction, you want to break the circuit until you're ready to measure. Then you connect it, you get a number. Now, typically the number will start off here and it'll go up like that, and then go back down. Just the nature. That's not chemistry, that's engineering. Okay, salt bridges and porous discs, they are the connection, one of the connections between the half cells. The salt bridge needs to contain a strong electrolyte, produces lots of mobile ions. And we usually keep them from just wholesale mixing. One way, and the way we're going to do it, is to put those ions into a gel matrix. We're going to use agar. Anybody here have microbiology? Okay, so you know what agar is. It's made from seaweed. I tried to use gelatin before and it didn't work. Jello, because Jello is made from a protein. The proteins have their own ionic character. Agar is neutral. Okay, so we get those the salt in the bridge fixed by this agar. Well, the other way you can do it is you can fill up the tube with a liquid and then plug the ends with something like glass wool, or even put an agar plug at the end. What that would do is reduce the overall resistance, actually. But we're going to do it the old-fashioned way. And the porous disc is there. Okay. So if this is where oxidation takes place, there must be a reducing agent in there somewhere. And on this side, since this is reduced, there must be an oxidizing agent here. Now, we've also got names for these things. The cell where oxidation takes place is called the anode. And the site of reduction is called the cathode. Okay. So how do you keep those straight? I don't know if any of you are old enough to remember CRT terminal displays for computers. They look like little TV sets. You can see pictures of it on the internet. But they were heavy, right? Computers were not portable. So you had these, they look like little television sets. Have you seen the old television sets with big boxes, right? They have the CRT or cathode ray tubing. That's how they operate, rather than flat panels. Well, the cathode ray tube produces a stream of electrons from a cathode. So if we think of this as the cathode, it's producing a stream of electrons into that solution. So this side is the cathode. That's the way I remember it. And then the other one is the anode. By convention, the cathode is on the right. Now, we may run across some instances where they put it on the wrong side, but most of the time you'll have the cathode on the right, the anode on the left. All right, how about cell potential? What do we mean by cell potential? Well, we actually mean voltage, volts. And we use a fancy E for the cell voltage. Electromotive force is what that stands for. So it's a driving force for moving electrons. How big is the push to move those electrons? And so if you have household current, the push behind that current is rated at 115 or 120 volts. If you've got a washing machine or a water heater hooked up to the electricity, it's probably 220 volts. So it's a bigger push. If you go out and climb one of these power poles and grab onto that line over there, you're probably going to get 10 or 20,000 volts on these lines. I think cross-country lines are going to be like anywhere from 100,000 to 1,000,000 volts. The higher the voltage, the less there's loss of power in transmission. That's the way alternating current works. By the way, the voltage that you're given here is not maximum voltage. That's the RMS voltage, root mean square voltage. It's a way of converting the alternating current into its equivalent direct current. So the peak voltage out of that socket right there is probably 150 volts positive, and then it goes 150 negative. So they average out, root mean square averaging out at 120. If we had an oscilloscope, I could show you. You'd have to measure the top and the bottom. Anyway, this is the cell potential, the voltage that we can expect from our galvanic cell. And it will vary based upon what's the reaction going on here, what's the reaction going on over there. Those two put together will give you a certain voltage. If we change one of them, we'll get a different voltage. If we change both of them, we'll get a different voltage. If you change the concentrations, you'll get a different voltage. So the first thing we're going to do is look at standard potential under standard conditions, and we have to define what those are. And then we work from standard conditions to actual conditions. And that's where the Nernst equation comes in. Okay. The unit of electrical potential is the volt. Right? So what does the volt mean? The volt means that with 1 volt, you can do 1 joule of work for every coulomb of charge that is transferred between point A and point B. Coulomb is a measurement of charge. So 1 volt equals 1 joule per coulomb. Coulomb's named after a Frenchman that worked with electricity. Now, the thing about the coulomb is it's a standard unit of measure for working with electricity. But for conversion to how do we convert that to moles of electrons that are moving? There's a conversion factor. Oh, well, it's going to be hard to hear this with that fan blowing, but I'll put the original, I'll put it in the Bright Space video. Let's see if we can hear it. Let me get to...
A useful galvanic cell can be constructed by using zinc and copper. The anode is a zinc bar placed into a zinc sulfate solution. And the cathode is a copper bar placed into a copper 2 sulfate solution. two solutions are connected by a porous sodium chloride salt bridge that prevents the two solutions from mixing but allows ions to migrate. Attaching the cell shows that electrons flow from zinc to copper. Because zinc is a more active metal than copper, it is more likely to lose electrons. For this reason, the zinc bar is oxidized, producing a zinc ion and 2 electrons per zinc atom. The copper ions in solution gain 2 electrons and are reduced to copper metal. As the reaction continues, excess positive zinc ions build up in the zinc solution. At the same time, the loss of copper ions from the copper sulfate solution creates an excess of negative sulfate ions. Positive sodium ions migrate into the copper sulfate solution from the salt bridge, while negative chloride ions migrate from the salt bridge to the zinc solution and maintain neutrality of the solutions. The reaction stops when the zinc bar or copper ions are depleted. The overall cell reaction can be written like this.
Okay. I'm gonna leave that off until it gets hot. So the salt bridge is in there to neutralize charges because you're building up, if you're losing electrons here, you're building up positive charge on this side. So you need negative ions from here moving in. On this side, you're building up negative ions. So the positive ions from your salt bridge move in there to neutralize the charge. So that brings up another point. If, let's see. If we're moving negative ions into this side and positive ions into this side, what if your salt bridge were composed of sodium and chloride? Okay. And suppose this side had a silver electrode. So as the silver is oxidized, silver ions migrate into the solution, right? Well, the silver positive ions migrate here and they have to be neutralized by a negative. So chloride ions move in here and what happens? It precipitates, right? So if it precipitates, that means you're not going to be able to reverse this reaction. I mean, it'll still work, but those chloride ions are going to precipitate out that silver as a solid, and now it's effectively removed from the reaction environment. Okay. So measuring cell potential, let's see. I'll leave that up there. You can measure it with what we call a voltmeter. There are several ways to measure it, several instruments that can use to measure voltmeter. Voltmeter is probably the cheapest. You can go to Walmart and buy a voltmeter for what? $5, $10 most?
I think they're about 15.
15? Okay. Yeah, thank you, Joe Biden. But the voltmeter measures voltage by comparing. It has a built-in resistor of accurate known resistance, and it uses Ohm's law. If I can remember, I can write Ohm's law. Let's see. Okay, so I is current. This would be coulombs per second. Voltage, right, would be joules per coulomb, and resistance would be in ohms, right? The omega symbol, the Greek omega symbol. All right, if we know exactly what this is, and our device can measure accurately the movement of current, then it electronically calculates what the voltage is. This is the cheapest way to do it. The problem is there's internal resistance in your meter too. So you don't get a maximum value of voltage. You just get the voltage that's measured. Okay. The maximum cell potential can only be determined when the current is zero. And if the current's zero, we can't use the voltmeter, right? Because it depends on a current value to calculate the voltage against a known resistance. So if you want the maximum cell potential, you got to use a different device. That device is called a potentiometer, right? Potential, cell potential, we use a potentiometer. What the potentiometer does is it goes in the circuit and it has a built-in reverse voltage. So we apply enough voltage in reverse so it stops the current. And when the current goes to zero, the voltage that we've applied is the maximum voltage. So potentiometers are more accurate for the maximum voltage, but they're much more expensive. And they have to be calibrated frequently. Okay, so we use the voltmeter or the multimeter now because you can do a lot of stuff with the meters. There's a picture of one in your method. I don't know if I'm going to use that one. I've got a couple of others that are in the kit. I think that's the one I use at home. I just had it handy when I took a picture.
My husband's an electrician, so.
Oh, okay. So I'm not telling you a lot of new stuff now, am I?
No.
You probably get an earful anyway. Okay, so here's a digital voltmeter, and we hook it up to the circuit, and the voltmeter is in the circuit, and the circuit's complete, so we should get a value. And the example here gives you 1.06 volts. Now, if we put the half cells in the correct position, then that voltage is going to say the electron movement, the current, the electron movement is this way. I think when I studied this stuff as a student, current was opposite to electron movement. Current went from positive to negative, and the electrons go from negative to positive. Now I think they may have resolved that issue, because originally, when all this was being developed in the late 18th century and in the 19th century, they didn't know what the charge carrier was. They thought it was positive charge. So the current was based upon positive charge movement, and now we know it's not. It's based upon negative charge movement, electrons. All right, so we always had to consider current goes this way, electrons go that way. Okay, standard reduction potential. This is the potential you should expect from a cell under standard conditions. So all the solutions are 1 molar in concentration. And if there are any gases involved, you can have gas electrodes too. If you bubble a gas through in one of your cells, then the gas pressure would be 1 atmosphere. It's just enough to deliver the gas to the tip of your electrode. And then as it's being consumed, it'll use more. So 1 atmosphere pressure is required. So we put these in tables. We put voltages for half reactions of this one, half reactions of that one, and they're always listed as reductions. So standard reduction potentials in a table, and they're coming up on subsequent slides, are given as reductions. So you're going to have something yields something else plus the electrons. Excuse me, it's the other way around. All right, that's oxidation. Something plus electrons yields something else. The problem with that is we already know that you can't measure a half cell potential. It's got to be a complete circuit, right? So 1 half cell won't do it. So what we do is we decide on a standard. and compare everything against our standard. And the standard is the standard hydrogen electrode. And the hydrogen electrode is taken as 0 volts. So whatever we measure is considered the voltage for the half cell. Now, depending on what is in one of the half cells, the hydrogen electrode may be on this side or it may be on that side. It just depends. But we take hydrogen as 0. Then now that we know the half cell voltage for each one, we can combine them in any combination we want and theoretically determine what is the voltage for our galvanic cell with that combination. All right. So we need a lift out temperature. Standard temperature is 25 degrees. In your book, well, it was table 18.1. I'm not sure what it is now. But it's got all the half reactions that you're going to need there. So if we need the half reaction as a reduction, right, then that reaction will go on this side. If we need it as an oxidation for the other cell, then we have to reverse it. Right? We have to flip it around, put the electrons on the other side. When you do that, all you have to do is reverse the voltage. Just change the sign. Then you can add them together and determine what the cell voltage is under standard conditions. So I said this one, when a half reaction is reversed, you just change the sign. When a half reaction is multiplied by an integer, the standard potential does not change. Because the standard potential is an intensive property. It doesn't matter how much. So you could have a cell this big, or you could have a cell this big. It would have the same standard potential. Now we are going to calculate voltages as extensive properties. That's where you change the concentration from the standard from 1 molar. When you change the concentration, then you change the value of the voltage. Right, we'll get to that. So we just finished a chapter on spontaneity. Under what conditions does how does the galvanic cell run spontaneously? When you measure a positive voltage, that's the spontaneous direction. Positive voltage means spontaneous. How about delta G? Negative delta G is spontaneous. Right? All right. We'll work on the proof later. So here's part. I had to break the table apart. So here we start with the standard reduction potential for fluorine reduced by 2 electrons to yield 2 fluoride ions, is 2.87 volts, measured against the standard hydrogen electrode. So if the voltage is positive, right, if you have a standard hydrogen electrode, which would be hydrogen gas, let's see, plus, no, standard hydrogen electrode is going to lead to 2 hydrogen pluses plus 2 electrons. So the standard hydrogen electrode is an oxidation. So if we put that together with fluorine, then the fluoride is plus 2 electrons, yields chloride minus 2 of them. Like that. Put those two together, and since this one is 0 and this one is a positive 2.87, right? Then we would leave them exactly like that. We would leave the fluorine reaction as a reduction, and we would leave this one as an oxidation. It's going to be 0 in both directions, isn't it? Right? Change the sign. What number do you get when you change the sign on zero? Trick question. You get a zero, right? So it doesn't matter which way you write the hydrogen, whichever way you need. So if we add these two together for our galvanic cell, we get positive 2.87. So we write, that means that fluorine in this direction as a reduction is the preferred way for our cell in this case. It gives us a positive 2.87. That's spontaneous. If we went down to, let's see, one of these negatives, right? There's our standard hydrogen electrode. They can the other direction. If we went down to, say, I don't know, lead reduction is a minus 0.13. So lead being a minus 0.13 volts as a reduction, we'd have to flip the lead to an oxidation to get a positive value. So the lead would have to be oxidized. It would have to be over here in order to get a spontaneous reaction. And there was mention in that video of a more active metal. It just means the metal is more likely to be reduced than others. So this copper actually goes the other direction. If we go from the metal and oxidation, then the more active metal would be down here, this lithium at minus 3.05. It doesn't want to be reduced. It wants to be oxidized. So lithium in this list is the most active metal. And then we should find zinc up here somewhere. There's zinc at negative 0.76. And then we go back up to zinc, which was also in that video. And zinc is listed as, I missed it. Where's zinc? Maybe it's down. Oh, there it is. 0.76. So the more active metals are lower, more negative in our table. And the less active ones are above. So the less active ones are the ones that are going to be reduced, and the more active ones are the ones that are going to be oxidized in a pair. Put them together. All right, now how do we use that table? Well, in order to calculate the voltage of a cell, and we want a galvanic cell has to be written so it's spontaneous, with the standard cell potential is, you can do it this way. Standard cell potential is equal to the standard potential of from the chart for your cathode minus the standard potential for the anode. Now, why is that? Well, the cathode, since they're all reductions, the cathode is still going to be a reduction, right? So we leave it alone. But the anode is written as a reduction. Now it needs to be an oxidation. So we got to flip it. That's why we have to change its sign. So cathode minus anode gives you the cell potential. That's one way to do it. Just memorize that formula. The other way is to look at your arrangement. Let's see, I need an example. Let's see. Standard reduction potential. Okay, here we go. So if we write the half reactions for this iron and copper cells, half cells, there they go. All right, so you've got these two half cells, one's in one side, one's the other. Which one needs to be sign changed to give you a positive summation? If you make the iron negative, if you switch it to an oxidation, that's a higher negative. You're going to get a negative 44. No, 43. A negative 43. That's not spontaneous. So the one that needs to be flipped is the copper. It needs to be the oxidation or the anode. And that changed the sign to negative 0.34. Oh, you gotta go. Oh, I still got wait a minute. We have lab today?
No,
Oh, that's on Thursday.
yeah.
Okay, I'm gonna have to
Which
shut
means
up then.
there's-
Okay, I guess I'm gonna have to stop here. Right? Or
Usually have lab on Thursday, so. Today is Thursday.
today is Thursday? Oh,
We have lab.
okay. So I'm gonna keep going. Okay, so picking up where I left off, the one that needs to have its sign changed is the smaller positive one in this case. A negative 0.34 and a 0.77 gives us a positive 0.43 volts. So if we put the copper in the anode, we flip that equation and we leave the iron alone and put it in the cathode, we'll get a spontaneous voltage, a positive voltage. So that's the way I think about it, rather than trying to memorize that formula. Which one needs to be reversed to give us an outcome of a positive voltage? That's the way I look at it. Okay. And by the way, how many electrons moved? Well, we look at the equation, right? Iron would have to be double, right, to account for all the electrons. But the standard voltage is still the same. But the number of electrons that moved is 2. 2 moles of electrons moved in this reaction. Okay, so keep that in the back of your head. So here's the overall balanced equation, and the voltage that is given is 0.43 volts. So plus 0.43 volts. What's a standard dry cell voltage? 1.5. Yeah. Dry cells, whether they're D's, C's, double A's, or triple A's, they're 1.5 volts. Now, have you ever measured one? No. Measure one and you get about plus 1.65 volts. So they're guaranteed 1.5 volts, but they actually produce 1.65 until they start to run down, and then they'll go to 1.5 and then lower and lower and lower till they're no good anymore. They're one use, toss them. So the calculation of the actual cell voltage uses this equation, the Nernst equation. And believe it or not, it's named after a person whose name is Nernst. I think he was German. And we need to know the stoichiometry so that we can, the balanced equation, so that we can tell how many moles of electrons moved. That's essential for calculating the actual voltage. If we know the standard voltage for our cells, then we need to know 2 things. We need to know the number of electrons, the moles of electrons that move, and we need to calculate the Q for that balanced equation. That'll come in a few minutes. So let me clear the board. I'm gonna have to turn the fan back on. I'm starting to sweat. Yep, 75 degrees. I don't think I have any more videos. All right. If we look at this question in terms of, well, just what is the question? Order the following from the strongest to weakest oxidizing agent. So what does that mean? If it's an oxidizing agent, the strongest oxidizing agent is the more easily reduced. So if we have the reduction equation, or any of these elements or ions, then the one with the highest, the most positive voltage will be the one most easily reduced. Because positive means spontaneous. So if we were to write them out, what would that look like? Well, we'd have iron. And reduced, we'd have to add probably 2 electrons to go to iron 2 minus. Sodium, we'd have to add, maybe we ought to use 3. And then sodium would only take 1 electron, if at all. And then fluoride, fluoride ion plus 1 electron would yield. We're not doing so well, right? Because metals don't want electrons. And fluoride's already got its electron, it doesn't want any more. So we're not doing too well. How about this one? Now we're getting somewhere. Plus 1 electron yields sodium solid. That looks pretty good. And then chloride plus 2 electrons yields 2 chloride. Okay. So the most easily reduced would be one of these guys right here. Right? So let's see. We don't know the values for sodium, fluorine, and iron. Because they're not written that way. We don't have reduction potentials. We have to make some assumptions. We do know the other direction. So if we had we do know this one as a reduction. All right, those are the values that are given in our standard reduction tables. So if we flip this one around, what's that voltage? We don't know. So this is an unknown voltage. Right? How about sodium? Well, sodium is an unknown voltage too. How about chlorine? You know that 1.36. Okay. And iron, we don't know that one. Sodium, we already do, yeah, we already did sodium. Oh, I got 2 sodiums up there. Okay, so which one would be most easily reduced? Chlorine? Yeah, I think chlorine would be the most easily reduced. So that's going to be the best oxidizing agent, chlorine. The worst is going to be sodium. Why? Because sodium is way over there. It's an alkaline metal. And if anyone doesn't want to be reduced, it's alkali metals. They'd be more likely to give up an electron than accept one. That's why we put iron, sodium on the far right. Then iron is a little bit better at reduction. Not much better, but a little better. Okay, the sodium ion will accept, and we have a value for it. Right? Yeah, minus 2.71. So it's not quite as good as chlorine, But sodium ion is okay. Are those the only ones we have? Where does fluoride go? Fluoride's even worse because it's way over here. Fluoride is the most electronegative element in the chart. So when it gets its electron, it's happy, doesn't want it. So it's probably the worst oxidizing agent of all the bunch. All right. That didn't teach us a whole lot, did it? This gave me something to talk about. Let's get on to something we could use. Probably ought to nix that slide for the whole thing. It doesn't, really doesn't help. There's a shorthand way of writing a galvanic cell called line notation. By convention, the anode's going to be on the left, just like we drew our big picture. So the anode reaction is going to be on the left, and the cathode reaction is going to be on the right. And we separate them by a double line. That means they're in separate containers. This represents either a porous disk or a salt bridge. Okay. All right. A single vertical line is used anywhere we have a phase difference. So if we had, let's see, we've got an example here coming up. And then we write the concentrations in there if we know them. So in this example, we have the anode on the left. We have the magnesium. We write the magnesium here first, and a phase change to the magnesium ion. Like in aqueous solution, this is a solid. And then on this side, we have the aluminum ion in aqueous solution with a phase change to aluminum electrode. Now, why do we write them that way? That's so that we can, in our minds, think of electrons moving from here to here. Okay. So we're not given concentrations here, but if you know them, write them in. There's the anode, there's the cathode for this line notation. So what if we have an electrode that doesn't participate in the reaction? Here, everything here is part of the half cell reaction. We put that in. Say if we use the platinum electrode, we would put in over here. Right there. But not for this reaction. That's just where we put it. If it were on the anode side. So let's describe this galvanic cell based upon these reactions, right? So we have silver that's being reduced to silver solid. Okay. And we have iron that's being reduced to iron metal, like that. And the standard reduction potential for silver is 0.80, and for iron is 0.77. Okay. So which one is the anode, which one is the cathode? Which one needs to be flipped so that we get a positive summation? That one right there, right? Like, make this one negative, you still get a positive outcome. So we would write this one like that. That would lead to this plus this, and the voltage there would be a negative 0.77. So we take this one plus that one, and we get a positive 0.03 volts. 30 millivolts, that's not much. But that's the spontaneous voltage. There we go. And the overall reaction equation would be, oh, I made a mistake. I sure did. Because we only did one electron. And we went to 2 plus. Nobody caught me on that. You guys need to be more diligent. Now we've properly described. That's the standard voltage for this cell under standard conditions. 0.03 volts. And how many moles of electrons moved? Just one. How would we write this as a line notation? That's not part of the slides, but we want the anode on the left and the cathode on the right. Cathode's reduction. So we have our salt bridge and we have the silver electrode over here. And we have the silver ions here. And on this side, we have the what? This is giving up. And this is what's left over. Right? And the electrons are moving from here to there. So when there's no phase change, you just put a comma. There's no, these are in solution together. So what we need is maybe a platinum electrode. Well, actually, that would be the phase change. This will be platinum solid there, like that. And the electrons would move from here to there. Okay. All righty. Let's see, what do we got? Receives electrons and loss in electrons. All right. Well, there's what it would look like in a picture form. I chose the right electrode, platinum. And we would have 1 molar this, 1 molar that. So we could say 1 molar, 1 molar, molar. And we're using a porous disc instead of a salt bridge for this description. So what would our counter ions be? Right, because you still have to move ions to balance charge, right? Since we have no counter ions in the salt bridge, we have to put them into the solutions, right? So what will keep silver, what will keep silver in solution? Nitrate, that'd be my choice. So our counter ion here would be nitrate, probably. How about our counter ion here? Why don't we just make them both? Yep. Just make them both nitrates. All nitrates are soluble, so that would be a good choice. So as we remove silver from solution and make this solid, then that removes the positive ions. And as we produce iron 3 plus ions, it's going to migrate through the porous disc. Never had considered that. You know, could that be a problem? What if we had here we go. let's make this potassium nitrate. Now potassium can do the migrating. And because these guys are busy in the reaction, so the potassium can move. And this would be just silver nitrate. Because the nitrate's going to move from this one over. So that would be silver nitrate in solution here. This would be potassium nitrate. We could make iron 2 plus nitrate in solution. We would have to have some 3 plus probably in there to get it started. Okay. There's your line notation. All right, I left out their phases. So it'd be aqueous, aqueous, aqueous. You gotta get that one right. Solid and solid. All right. Let's see. This is just restating some stuff. All right. Sketch a cell, you following electrodes. So we have silver on one side, copper on the other. We have to find out which one's which. Like which one's the anode, which one's the cathode. So we look at their voltages. The voltage, the anode's going to be copper. So copper is the one that has to flip. And in the salt bridge, we use sodium nitrate. There we use nitrate again. Because if we use chloride, we're going to precipitate the silver. Okay. So, yeah, if we start off with 1 molar on both sides, and we need actually a balanced equation would be good. So let's do that. Let's take the picture and construct a balanced equation. All right, so on the right-hand side, we're going to, oh, by the way, the cathode side is where we take the silver ions and we turn them into a solid by adding electrons to them. So what does that do to the mass of the electrode? No idea? If you take silver out of solution and precipitate it, reduce it, put it on the electrode, what happens to the electrode mass? It goes up. And conversely, on the other side, we're taking copper atoms and we're stripping them of their electrons and putting them in solution. So the copper electrode's mass goes down. So that's one way that you can tell how far the reaction has proceeded. Right? You just weigh the silver electrode before you start, run it for a while, weigh it again, and you see how much mass was added to it. Are y'all deserting me? You want, oh, starvation. Yeah. Okay. Okay. So let's get back to the question. What happens if we increase the copper ion concentration in solution? It starts off at 1 molar. So what happens if we increase that concentration? All right, let's look at it in terms of Le Chatelier's principle. Okay. We can take that reaction as is. Copper yields copper 2 plus ions plus electrons. Right, so say that's in equilibrium.
I put my cross there.
I'm sorry.
My cross there.
Oh, okay. Yeah. So if this is an equilibrium, we've got it established here at 1 molar concentration. If we increase that concentration, go back the other direction, aren't we? We increase the concentration in the anode. Then we drive the reaction to the left And that decreases the number of electrons that can move. So the voltage should go down. Okay. If, on the other hand, we make this one more dilute, say we cut it to 1/10 molar, then the reaction is going to proceed this way preferentially and produce more electrons. The voltage should go up. All right. Now we'll digress for a minute and introduce some concept of work. We know, let's see, spontaneous cell potential is positive. Spontaneous work is negative because of delta G. Delta G0 is negative for spontaneous. And that's a measure of maximum work available. So, in order to equate them, we have to introduce a fudge factor. So we know that by definition, Q is the charge. I know last semester Q was heat, now it's charge. Okay. This is charge in coulombs. Okay. So remember what I said about voltage. 1 volt equals a joule per coulomb. Well, if we account for all the signs, then this work factor in joules, we have to apply a negative to it so that we can get a positive electromotive force. So if W is negative, work is negative. If we're going to do work, we have to, let's look at the system versus surroundings, right? If the system is doing work on its surroundings, that's a negative value. Negative W. That's what we want. We want to be able to do useful work. So the W has to be negative. So in order to make it spontaneous, we have to apply a negative to that W to give us spontaneous voltage. That's a better explanation. So if we solve for work, then negative work is going to be E times Q. Good, I can do better than that. There. E times Q. And the maximum, of course, would simply be, what's the maximum voltage? Remember, the maximum voltage is only if there's no current. So if there's no current, you're not going to get anything happening. So that's a theoretical maximum. So I showed you this one before. This is in voltage, this is in volts, this is in joules, and this is in coulombs. So voltage is an expression of the work that's performed per unit charge moving. So if we have, let's look at this as, let's see. Maybe it'd be easier to look at it this way. If we increase, if we need more work, we have 2 options. Since this is a direct proportionality. Actually, it's inverse. If we want more work with the same number of coulombs charge move, then we need a higher voltage. So you get more work for the same number of electrons moving if you have a higher voltage. So a higher voltage is good. Or you can have the same voltage and you need more coulombs moving, more charge moving. That means you need to increase the size of your reaction to produce more electrons moving for the same voltage. That's 2 ways to get more work out of it. Okay. So, but in any real spontaneous process, some energy is always wasted. Mate, we know that from the last chapter. Right? We waste energy, if for no other reason, we waste it in producing disorder. Right? Entropy. We increase the entropy, that's wasted energy. So the actual work will always be less than the potential maximum. And there are other factors that enter in there also. Okay, so W equals minus Q minus QE. Okay, there we go. That's equation. So if we make this actual values, now we're talking about the real world. So the work that we can get from a reaction is minus Q times. We just put the minus on that other side. All right, here's that conversion factor I was talking about. This is in coulombs. If we want to convert moles of electrons to coulombs charge so that we can apply this equation, we've got to use that factor, 96,485 coulombs for every mole of electrons. So if we find out how many moles of electrons are moving in our reaction, then we can convert to how many coulombs, what coulomb charge is. And the coulombs would go in here along with the voltage, and we can calculate the work.
So if there's 6 moles of electrons moving, then you would divide that 6 by the 96,000.
96,485, 96,485 is coulombs per mole. So we want to cancel the moles. So we would multiply by 6 moles of electron. The number of coulombs then would be 6 times that value. Yep. It'd be about, I don't know, 580,000, like that. Okay. Also, any change in free energy is an expression of the maximum amount of useful work that you can get. That's where this comes in. That's equal to W max. Well, actually, if this is negative, that would have to be that. Make that negative. That's the maximum amount of work you can get from the reaction. If we know delta G, W max is delta G. Actually, let me just get rid of these. There you go. For a galvanic cell, then, W max is also equal to minus QE. So delta G, that's the maximum amount of work that you can get from the cell. It's equal to delta G. And since Q equals number of moles times the Faraday constant, this is Faraday constant right here. This is the number of moles of electrons. And that's equal to the charge in coulombs. So Q equals NF. Number of moles of electrons times the Faraday constant yields charge. Number of coulombs moved. So that being the case, this is equal to, let's see, delta G equals, delta G equals minus QE. And Q. Here, Q. Q equals N times F. So if Q equals N times F, N times F. times E. That's equal to delta G. So delta G equals negative NF times E. Okay. There's Michael Faraday. He was, I think, 18th century, 19th century, middle 19th century. Michael Faraday was self-taught. He didn't have a college degree. He studied, he went to lectures. He just had a mind like a steel trap. And he had a very inventive mind. He was, in his day, he was known as the best experimental physicist of the day. In other words, his experiments were so simple, yet yielded so much information. That's where his reputation came from. And eventually he was inducted into the Royal Society of England. That was, you didn't get that from non-college educated people, but he made it. All right. So here we have delta G. If we're using standard potentials, right, then delta G0 equals minus N times number of moles of electrons times the Faraday times E. So since the galvanic cell will run in the direction that provides positive E, that means that we do have spontaneous, because that will give us a negative delta G. And we know negative delta G is spontaneous. All right. So here we have a concentration cell. Notice that the anode and the cathode are the same chemical reactions. The difference is concentration. So let's see if we can make sense of this. That's the only difference between the two, is the concentrations. We have the same silver electrode in both of them. And remember Le Chatelier, if we write the equation as the anode would be the oxidation step. Okay. Sulfur, it's silver plus an electron. So if we want to produce more electrons at the anode so that it can go over to the cathode, then we need to reduce the concentration of silver ions in solution. So that's what we've done in the anode. We've made this small, so if the reaction runs this way, produces electrons now that go over to the other side. And when they get there, they're going to see silver ions in solution. And those electrons that are being transferred are going to add to that silver ions and make silver solid. So what we've done is we've increased the number of electrons moving, drive the reaction toward the solid on the cathode side. Okay. So as a rule of thumb, if you have a concentration cell, the electrons are going to move from the low concentration to the high concentration. The anode is the low concentration, cathode is the high concentration. Now the voltage won't be very high. In fact, when we create our concentration cell in the lab, you're going to be measuring voltages in millivolts. And your meters will do that. You just have to switch the scale. You know how to do that. Okay, here's Walter Hermann Nernst. I guess he was active late 19th century and into the 20th century. He did lots of different things. In those days, chemists, physicists, whatever, they were kind of interchangeable. They were called natural philosophers. But he worked in thermodynamics, physical chemistry, electrochemistry, solid state physics, probably in his later years. And he got a Nobel Prize for thermodynamics. Let's see. And he proposed the Nernst equation actually early on. It was like, okay, if he was born in 64, that being 23 years old, right? So that's when the scientist is hungry and trying to make a name for himself so he can retire later. Einstein did the same thing. In his early 20s, he came up with his most groundbreaking theories and the ones that got him a Nobel Prize. And then later on, somebody asked him, because in his golden years, he was still working on a unified theory of physics, so that a single theory could describe everything. Instead of dividing classical physics into Newtonian, and then get down to the small world, and we have to go quantum mechanics, get to the big world, and we have to go Einstein's relativity. He wanted to unify all of those into a single theory. Somebody asked him, why are you doing that now? He says, because I can. I can afford to. I've made a name for myself already. You know, young chemists, young physicists, they've got to work on stuff that'll produce results. And so, but now, you know, I'm established. I can spend all my golden years working on this unattainable project. Anyway. All right. Did we mention what the third law of thermodynamics was? I think we did, didn't we?
Last chapter.
Yeah, last chapter. It's the one where is entropy zero? It only occurs at absolute zero for a perfect crystal. And his work was instrumental in developing that third law. I don't think he proposed it, but it was based upon his work. Okay, the Nernst equation. So now what we're going to do is take the actual concentrations of reactants in our half cells and use those plus the standard potentials and the moles of electrons that move to determine what is the actual voltage for our cell. Right? And here's the equation that he came up with. And let me get rid of some of this mess. I'm sure there was a whole lot more to it than just this one equation. Right? When he proposed it, he probably had to write a paper and have pages and pages of calculations to prove it. But we're the beneficiaries. So you can calculate the actual voltage of your cell if you know the standard voltage of your cell. And then you subtract this value, RT over N, Faraday constant, times the natural log of Q. So in order to do Q, you have to have the balanced equation. Then you have to know the concentrations of your reactants and products, calculate your Q. Then you have to know how many moles of electrons were moving in that balanced equation. You have to know the temperature in terms of Kelvin. And then the R will be the one with energy, 8.3145. And then you have to know the standard potential. And if you know all those factors, you can calculate the expected voltage from that cell. Well, under most conditions, this one's going to be 298. Okay, 25 degrees. That's a constant already. This is going to be an unknown. This is a constant. So we can combine this one, this one, this one into a single constant. We could take RT over F into a single constant value. And then we also want to convert this into something more usable. Like instead of natural log, let's convert it to common log. Right? And that requires another factor times out here to do that. Once we got all those values, then we have a simpler equation. And that's this one. Oh, that factor X is 2.3026. So once we multiply all those together, we get 0.0591. 0.0591 over N, right? The number of electrons moving. And then the common log of Q. So that was a little more manageable. If we were going to vary some of these other factors, then we'd have to use that one. But for our purposes, we're going to use this one. We're always going to be at 25 degrees. We're always going to have the same Faraday constant, the same R, and we're going to use common logs instead of natural logs. So that's the equation we're going to use. And then I've got something over here just to prove that my 2.3026 conversion factor is accurate. You don't have to regurgitate that at any time. I'm just proving that's how you convert from natural log to common log. All right. So how about the Nernst equation? At 25 degrees in equilibrium, if Q equals K, then E equals 0 because it's at equilibrium. So if you calculate your Q and it equals the K for that reaction, then you're not going to get any voltage. But we can also use, now you won't get any actual voltage, right? This will be 0, but you still have a value for this one. Right? And if this is equal to K, and we know the number of moles, then we can have an equation where, let's see, that's a negative, so we're going to make it a positive because we're moving this one on the other side. Then we'll have 0.0591 over N times log K. So if we know the standard voltage, we know the number of moles of electrons moving, we can find out what the K is for that reaction. And when Ks are reported in the literature or in reference manuals, sometimes this is the way they do it. They determine the standard potential for a reaction and then calculate the K, and that's what they report. They don't have to measure the K, they measure the voltage. Or they use the standard voltage. All right. So this is a short way to say it. We get equilibrium constant from cell potentials. So for this oxidation reduction reaction, S4O6 2-, that's what that's called. That may not have been in our list. S2O3, I know that one is thiosulfate. The appropriate half reactions are given right there. And then we want to find out what K is. All right, so we need, we have to add those two equations together in such a way that we get the overall equation. All right. And really all we have to do here is decide which one is oxidation, which one's reduction, and then how many electrons are moving. So what about 2? How many electrons? Oh, 2 moles of electrons are moving, right? 2 moles of electrons. And since we're looking for K, we don't have to have the accurate balanced equation. We just have to be sure that we've got the right number of moles of electrons and we have calculated the standard potential. Here, you know that, then we can calculate K. So it's a shortened pathway to the answer. So the natural log K is 22.6 in this case. So we just take the anti-log of 22.6. That should be right here. There it is. So our K for this reaction is 4 times 10 to the 22nd. And that's typical. when you have a spontaneous reaction with a positive voltage, the K is going to be large, positive large. Okay. What's the difference between E and E0? Well, when is E equal to 0? At equilibrium. Yeah, at equilibrium. When is E0 equal to 0? Ha. Oh, you're cheating.
We said we get to go.
No, we didn't say this one. E0 is 0 for a concentration cell. Yes, it's equal to 0 for a concentration cell. So if you set up a concentration cell, then this will be 0. And you'll have a Q because you have different concentrations. Calculate the Q, then you can find the voltage. All right. Okay, so this is an exercise in calculating the potential for a concentration cell where the nickel reaction is reduction and oxidation, but they're at different concentrations. So that's why our subscript is C for concentrate for cathode and A subscript for anode. So we can tell them apart. And there's our combined equation. So we have the cathode, we have the anode, cathode, anode, and we just need values. So if we have 1 molar for the cathode, that will go in the denominator. Right? Why? Because solids don't count. And the anode, let's see. Wait a minute, that's not right. Q. That should be reversed. Well, let's take a look at this again. Okay, cathode is reduction. So we got Ni2 plus cathode plus 2 electrons yields Ni. Okay, anode is Ni sub A yields, okay. And put them together, we get the cathode, solid anode equals the solid cathode plus the anode. Okay. Nickel concentration of the anode is 1 times 10 to the minus 4. Yeah, that's right. Yeah, okay. Anode is on the right, right? It's a product, so it goes in the numerator, and it's at the low concentration. So in the balanced equation, the anode concentration is on the right, but when we build our cell, put it on the left. That's what was throwing me. So they're in their correct proportion. 1 times 10 to the minus 4 divided by 1 is 1 times 10 to the minus 4 times 0.0591 divided by 2. Well, we have to take the log of it first. The common log of 10 to the minus 4 is 4, right? So 4 divided by 2 is 2, and 2 times 0.0591 is 118. So 0.118 volts out of this cell, or 118 millivolts. Okay, nickel electrode here and a silver electrode there. What's the question? Sketch the cell, show the anode, cathode, electron flow, and cell potential. Right, we can calculate the cell potential right off. We can't change the silver to a negative because that'll give us a negative voltage. So we'll change the nickel electrode, that will be the anode on the left. So our total voltage would be 1.03 volts. And there's our line notation. We put the nickel on the left because it's the anode, put the silver on the right because it's the cathode. And that's what the cell looks like. Okay. There's the voltage, right? We calculated that one in our head already. All right. We're just about finished. when we set up a galvanic cell or a battery, the reason that we would need a force disk or a salt bridge is because we don't want the solutions to mix. But what if the solution for the anode is the same as the solution for the cathode? Then you don't need the salt bridge. And that's the lead acid battery in your cars. Right? It has a common solution for both the anode and the cathode. The only difference is the cathode is lead 4 oxide and the anode is pure lead. Okay, so you get those alternating plates. And you have the negative electrode, of course, is attached to the anode. So the electrons come out that negative electrode and they go through your system and they end up back on the positive side, where the lead oxide plate is. And let's see, here's the overall reaction. And notice that both the lead and the lead oxide react with sulfuric acid to produce lead sulfate. Okay, so we get lead sulfate deposited on both of the plates. Right? So what does that do for recharging? Well, for recharging, you have to have access to the underneath material. So if you reach the point where the lead sulfate completely coats your plate, and now the solution can't get at the underlying plate, we say that the battery is sulfated out. It is dead and will not recharge. You have to recycle. So if your husband has a dead battery and he puts it on a trickle charger and leaves it there for 2, 3, 4 weeks and still not charged, that's probably what happened to it. It's gone too far. So the engineering construction of those plates also plays a role. You can get batteries with the same voltage, right? And each one of these cells is 2 volts. So the average car has 6 cells in it with 2 volts each. And that's one of the characteristics of electrical engineering. If you have a cell here, a cell here, and a cell here, I guess we need 6 of them. 1, 2, 3, 4, 5, 6. Then you have a positive electrode here, a negative there, positive there, and a negative there, positive, negative, positive, negative. Negative, and you connect the negative to positive and you cascade them like this. That's known as putting them in series. So when you have a series connection of 2 volts each, the total voltage is the summation of all of those. 12 volts. That's why the car battery is 12 volts. It has 6 cells in it, 2 volts each. Some big trucks that have big diesel engines, they need more oomph to get them started. They'll have not 6 cells, but they'll have 12 cells, and their battery will be 24 volts. That's what happens when you put them in series. If you've got lights on your Christmas tree and one of the lights burns out and the whole string goes dead, that means they're all in series. Because one goes dead and breaks the circuit. There's no complete circuit anymore. If one of them goes out and the rest of them stay lit, then they're in parallel. So you've got independent positive, negative for each one of your light bulbs. All right, let's get back to this topic. No need for a salt bridge. I mentioned that because the solution is the same for both of them. Let's see. All right, we're going to talk about this in just a second. When you recharge the battery, you're reversing the electron flow. That means you're driving the reaction in reverse. As written, it's spontaneous. But if we apply a voltage that's greater than 2 volts for the cell, then it'll go backwards. Or for this battery, if you increase the voltage above 12, then you'll run the reaction in reverse, and that's called an electrolytic cell. It's just the converse of a galvanic cell. The electrolytic cell is non-spontaneous. You're running it in reverse. There's a dry cell battery. I'm not going to spend time on this. Just to call your attention to that cathode has a graphite rod there because the reaction takes place in that matrix. Now, we call it a dry cell because if you puncture it, the stuff just doesn't flow out. It's not liquid. It's a paste. So it's not really dry. We have other examples. We have this mercury battery, which they don't use anymore for obvious reasons. So you have them in watches, hearing aids, small devices. Right? My calculator has a stack of, well, my old calculator has a stack of 3. My new calculator has a built-in chargeable battery, so I don't have to do anything there. But now we use a silver battery. Fuel cells. The nice thing about a fuel cell is it is a galvanic cell, but we can continuously supply the electrodes, the cathode and the anode with material. It never runs out until your tanks of hydrogen and oxygen run out. That's the good thing about a fuel cell. You can extract electricity from it, and then if you need more, all you have to do is refill those tanks with hydrogen. And usually the fuel cells don't have pure oxygen going in. They just take air and use the oxygen from the air. And there are various types of fuel cells. This is a hydrogen oxygen fuel cell. This is the kind that was used on the first spacecraft during the Mercury, Gemini, and Apollo years. They used fuel cells. So they had lots of oxygen, like for the astronauts to breathe, and that's why you've seen the movie Apollo 13. Right? When their oxygen tank ruptures, it wasn't just the oxygen that they were going to miss; it was the power, because their fuel cells ran off of that oxygen and hydrogen. So their spacecraft was dying. I think that's the way they put it. Corrosion. Corrosion is an oxidation reduction reaction. Corrosion simply converts metals to a compound. Metal is 0 oxidation state. We convert it to some compound with a positive oxidation state. We extract electrons from it, and that's corrosion. Most of the time, it's oxygen. But sometimes sulfur can enter into the mix. Nitrogen can enter in, but most often it's oxygen is part of the corrosion. And iron is notorious for it. You see an old tractor sitting out in the field that's been out there for years. If it's still standing, that's amazing because it's going to rust away. It converts iron to iron 3 oxide, Fe2O3. And you need moisture to do it, to set up that electrolytic cell. So the electrolytic cell is set on the surface of the metal. So steel, pure iron will do this. The only reason that stainless steel doesn't do it is because we mixed into it. Originally, it was 35% by mass. Chromium. Chromium is a more active metal than iron, so it will reduce. I mean, it will oxidize quicker, and it forms a chromium oxide layer on the outside of the stainless steel. Now the air can't get to it. That's what keeps it from corroding. So if you have a piece of stainless steel and you scratch it, the reaction is almost instantaneous. Seals that wound. There was a place in Atlanta called the Omni. It was a building that was built primarily for sports. And some architect got the bright idea, you know, there's a building material, it's iron, made out of iron, steel, that is specifically designed to corrode fast. Corrodes so fast, it produces a layer of iron oxide on the surface that keeps the water and oxygen away from the underlying metal. So that should work like stainless steel, only be cheaper. Well, the problem was, it worked. They put up the building, and within a few weeks, it was rusty red on the surface outside. Problem is, Atlanta gets probably 60 inches of rain a year. And there's a difference they didn't account for. Iron oxide is less dense than the iron or steel underneath. So it expands. Right? And that loosens its grip on the metal underneath. So when it rains, it just washes that rust off and it spreads across the concrete. You got red streaks everywhere. And it just continues to rust. So I don't think that architect kept his job for a while. Anyway, they tore that building down. It's not there anymore. It was ugly. Made an ugly mess. Okay, how do you prevent corrosion? Well, one way I mentioned already is you form an alloy that will preferentially corrode in substitution for the underlying metal. So alloying will do that. Stainless steel is good. Brass is good also. That's why they use brass on fittings on ships that go to sea in that salt water environment. Right? It will hold up against it. Let's see. What's other types of alloys that work? Can't think of any right now. Or you can just simply coat the metal with a more active metal. So I don't know if they, I think they still make them. They're just not too common. Galvanized steel buckets. Right? Galvanizing stuff. Galvanized nails, right? You can see those still. They just dip them in molten zinc. It's a layer of zinc on the outside, and zinc is a very active metal. So it may start off shiny, but by the time you get it to the store and sell it, it's kind of a dull grade from the zinc oxide that forms on the surface. So galvanizing will do it, or you can use a paint, a coating that eliminates the movement of water and oxygen from the atmosphere to the underlying metal. That has to be replenished periodically. Or you can use cathodic protection. So what's the cathode? Well, you want the cathode to be reduced, right? Because the metal is reduced. You don't want it to oxidize. So the cathode is the metal that you're trying to protect. So you connect it to a more active metal through a wire and let that metal corrode. And it delivers electrons through that wire to the other metal and keeps it from corroding. So they used to do that with buried gasoline tanks at filling stations. They have a buried magnesium electrode. They have to be big. And that would keep the tank from corroding over time. And you'll also see ships that have a belt of zinc or magnesium around them. And that's connected electrically to the ship. So that thing corrodes and delivers the electrons to the ship and keeps the steel from rusting. But as long as there's power in the ship can provide a trickle electron charge into that strip and keep from wasting the strip too. But when the engines are shut down and the batteries are down for servicing or whatever, then that strip is there to protect the ship. So the zinc will corrode instead of the ship. Here's a buried pipe, right, with a magnesium electrode that all right. So all you need is a metal that's more active than the one you're trying to protect. So magnesium works, zinc would work. Coatings, alloys, cathodic protection, okay, underground pipes. Which part's the cathode? Obviously, the pipe. Site of the reduction. Electrolysis. Okay, now we're going to look at electrolysis in. Yeah, still got time. So, yeah, that's a one. It shouldn't take that long. So we force the current to go backwards. We give it a voltage that's opposed to the spontaneous voltage, and we drive the reaction backwards. So here's one example, right? Electrolysis of water. If we electrolyze water, water normally would go from hydrogen plus oxygen to water. Just ask anybody who rode the space shuttle. Right? That's main engines of the space shuttle. Use liquid hydrogen and liquid oxygen. Came out of that big orange tank. But if we want to drive it in reverse, if we want to produce the hydrogen and the oxygen to fill the tanks, all we have to do is run an electric current through water. And at one electrode, you'll get, let's see, we can deduce which electrode produces the oxygen and which electrode produces the hydrogen. We just need to go backwards. Here's your gas, your oxygen gas. Okay, this is 0, this is 0, this is -2, and this is +1. So what are we doing here? We're reducing. So we're reducing hydrogen in water to hydrogen gas. In here, we're oxidizing. So we're going from -2 to 0. So when you put two electrodes in water, like we've got water here, and say we have a way to trap the gas. Got our electrodes here and here. They say this one, let's see, the anode would be the negative one up here. This would be the positive one because the electrons are moving away, here they're moving out. So at the negative electrode, you should get what? Electrons are moving away from the anode, that's the oxidation side. So here we should get oxygen. And here we should get hydrogen. Because this is the cathode. And the terminology is the same, whether it's a galvanic cell or an electrolytic cell. The site of reduction is always the cathode. So if we run the cell backwards, then they switch places. The anode becomes the cathode, and the cathode becomes the anode. Okay. Yeah, if you overcharge your lead acid battery, you're going to produce hydrogen gas. Because once you get the battery fully charged, then where does that electricity go? Well, it goes into the solution, the water. Right? It electrolyzes the water, and you produce oxygen and hydrogen gas. And if you don't have a way to vent it, it builds up and your battery explodes. So old batteries used to have vents in the caps. Right? They'd have 6 caps, and they have little pinholes at the top of them. So over time, especially if you overcharge a lot, your system's not fine-tuned, then you will lose water. You will lose acidity in your solution. So they have to be replenished. And full service stations used to keep sulfuric acid in a container and a hydrometer, and they would pull some solution out, and it would read whether your sulfuric acid was concentrated enough. And if not, they would add some to it. All right. So how is electrolysis useful? Remember, at the cathode, you are taking ions from solution and depositing them on the electrode as a solid. So on the, I guess the copper side, you would bring electrons into the copper electrode. They would take copper ions from solution, reduce them, and they'd attach to the electrode. So you could do that with other metals. You can coat metals with different metals. Have you ever seen a chrome bumper? No. You have to go to an antique car show now to see a chrome bumper. So this Saturday, go out to the airport and look at their cars. We're going to have a booth out there. I'm going to be there from Saturday noon till 3. They have antique cars out there. Some are pretty nice looking, and some of them have chrome bumpers. So their underlying is steel, but the outer surface is chromium. Right? And that keeps them from rusting and makes them look pretty. Well, it's a little more complicated than that because chromium won't stick to steel for very long. It tends to flake off. So what you have to do is you coat it with, I think you hit it with copper first, right? You coat the steel, right? Coat your steel with copper first. Then you coat it with nickel, and nickel is compatible with chromium. Then you chrome plate it. So say we want to coat a metal on an electrode. What do you need to know to determine how much of the metal is coated? Essentially, you need to know what's the current. Right? And by the way, I didn't mention this earlier. The measure of current is the amp, abbreviated A. 1 amp is equal to 1 coulomb of charge moving through past a point in a conductor every second. So 1 amp is 1 coulomb per second. If you know the current and how long it runs, and you know the reaction that it's based upon, right, at the cathode, then you can determine how much metal is deposited. That's what this flow chart is trying to show us. And you're going to need your conversion, coulombs to moles of electrons, 96,485 coulombs per electron. All right, so here's an example. Let's do this problem. And I think we're about at the end, aren't we?
Yeah.
Okay. So an unknown metal is electrolyzed. That is, it's deposited on something. It took 52.8 seconds. 52.8 seconds is equal to the time. At a current of 2 amps. Current here is 2 amps or 2 coulombs per second. That's what that means. And we plated, in that amount of time, we plated a mass of 0.0719. Mass 0.0719 grams. Okay, what's the metal? Oh, and the solution contains M and NO3, taking 3 times. Right? So what's the charge on the metal ion in solution? It's 3 plus, isn't it? Because this is -1, that has to be 3 plus to balance. So what we're doing is we're taking this 3 plus ion, we're adding 3 electrons, and we're producing the metal solid. Okay? So we've got the mass, we got the grams. What we need is the number of moles. If we've got the mass and the moles, then we can identify the metal because we can calculate its molar mass. Okay. So what we're getting at is how many moles is that? All right. So if we're running for 52.8 seconds, let's see, do I have the calculation here? Do I need to write it? Probably have to. Yeah, there it is. So here's that equation. This is in solution. We're gonna plate it out. And we know that our number of moles of electrons is 3. So 2 amps is equal to 2 coulombs per second. So if we know that the current is 2 coulombs per second, and we ran it for 52.8 seconds, then we know how much charge. Okay. Seconds cancel, charge. Now we want to convert the charge to moles of electrons. Right? So what's the conversion here? 1 mole of electrons is 96.485 coulombs. Okay. Now we got rid of the coulombs, we got the moles of electrons. Now we want to convert moles of electrons to moles of metal. Moles of electrons, moles of metal. What's the ratio? For every 3 moles of electrons, we have 1 mole of metal. So if we run that calculation, we should have 3.65 times 10 minus 4. Minus 4 moles of metal. Now we can calculate the molar mass. Grams per mole. Grams per 0.65 times 10 minus 4 moles. And so I don't have to get my calculator out. Round it off 197 grams per mole. So 197 would be gold. That's our metal. That's what they do to cheap jewelry. They electrolytically coat some base metal, usually with a lot of copper in it. They coat it with gold, electrolytically coated, it's just a few atoms thick. It looks nice and bright and shiny. And then after a while, your skin rubs off that layer of gold and you start turning green from the copper. Okay. Oh. Forgot about this one. So this problem was essentially a unit conversion problem from way back in the first semester. Wish there was a way I could impress that upon new students. Learn how to do those conversions because they're going to come back. Okay, consider a solution containing 0.1 molar of each of the following: lead, copper, tin, nickel, and zinc. What's the order in which the metals plates out as the voltage is turned up from 0? Well, if you look at each metal, and they're all 2+ charge, 2+, then we have 2 electrons, and that yields the solid reduction. So the ones that plate out first are the ones that are the least active. We want to, so they're going to have a voltage over here, standard voltage over here. Metals are going to form at the cathode because we're going to reduce them. So we got to oppose the voltage here. So how do we oppose the voltage? Well, let's see. This is a reduction. Right. The reduction potential predicts the order. The more positive the standard reduction potential plate first as the voltage is increased. So we're running voltage back that way. No, we're running voltage this way. Excuse me. Running voltage this way. We're going to plate out at the cathode. The more positive the EMF, the E value, are the ones that are going to come out first. And the more negatives come out last. Why? Because in order to oppose the voltage of going, let's see, Okay. Let's look at it this way. A positive voltage signifies spontaneous reaction. Right? So the more positive the voltage, we want to go this direction. So the more positive the voltage, the easier it is to get it to go that way. So all we have to do is induce it with a small voltage to get the most positive one to go first. Right? So let's see. Here are our voltages. There we go. Oops. There. So the most positive one is copper. It's going to come out first. Lead is the next one. Tin, close behind, nickel, and then zinc. And this can also be viewed as a reactivity series. The most reactive metal in that group is zinc. The next most is nickel, then tin, then lead, then copper. Okay, am I done? Almost. Oh, production of aluminum. That's an interesting story. When aluminum was first identified and isolated, oh, it was back 17th century, maybe late 17th century. The only way to produce aluminum was chemical means. You did a chemical reaction that produced aluminum metal. It was very expensive to produce large quantities of it. So the King of France, the story goes, when he wanted to impress his guests at state dinners, he wouldn't bring out the gold silverware or the silver, like gold flatware. He would bring out the aluminum because that was a sign of power and money. Aluminum was more expensive than gold because of that. Well, along comes, let's see. Well, these are commercial electrolytic processes. We'll get to aluminum in just a second. Purified metals, copper in the wiring has to be 99.999% pure to be a good conductor. Ask your husband.
No, that's why everybody wants to wire, they strip the copper.
Yeah, it's pure. Well, the production of copper from ore only produces about maybe 95% or maybe better purity. That's not good enough. So what they do is they dissolve it in, actually they hang it in plates and they electrolyze it. They migrate the copper through the solution from the poor plate to the pure plate. And they have suspended in there a pure plate of copper. And they run the current. They, at the cathode, they reduce the copper as it moves through the solution. And plates on that plate, and that's 99.999% pure. So they use electrolysis to purify copper. We are talking about metal plating, like chrome bumpers, that type of thing. I used to have a bicycle. It was a banana seat and high handlebars, and you could pop wheelies on it real easy. It had a chrome plated steel frame. You can produce industrial quantities of reactants, starting materials for other processes. We can take sodium chloride, salt, and melt it, and then electrolyze it to get the chlorine gas and the sodium metal out of it. This process was invented by, what is his name? Hall, James Hall, I think. He started doing this senior in high school, working on this problem. And he went to college and continued to work on it. Started off in his parents' garage with iron plates and explosive materials. He finally figured it out. He knew that he could electrolyze aluminum if he had enough power and he could get the aluminum into a molten state so that it could move the ions to the cathode. The trick was combining aluminum oxide, which is bauxite, it's the ore, aluminum oxide. We get most of it from the tropics. They produce bauxite down in the tropics and then ship it to Alcoa to purify it. And they need lots of cheap energy. So that's why Alcoa and the aluminum processors are located in the Tennessee Valley, where the government was producing cheap hydroelectric power, or in coal country, where you can get cheap coal to drive your steam generators and produce electricity. So as long as the electricity is cheap, the aluminum can be cheap. So what Hall and this Frenchman, Heroult, discovered almost simultaneously was that if you add sodium aluminum fluoride to the mix of bauxite, then it melts at a lower temperature. You know, instead of 2,000 degrees, it's less than 1,000, which is a big difference. That means you don't have to put as much energy into it to get it to melt. Once you've got it in that solution, or that liquid form, then you can run current through it and plate out the aluminum on these carbon electrodes. And it just, as the metal, it just sinks to the bottom. And then when you've finished a process, you just tap that plug at the bottom and out comes the aluminum. And it's so cheap now that we can make aluminum foil out of it and wrap our food in it and throw it away. But aluminum is extremely reactive. It takes a lot of energy to get aluminum loose from its oxides. That's why the cheap electricity is needed. And that's why when you throw an aluminum can out, 100 years later, it's still going to be there. Not because it's not reactive, but because it's so very reactive, it reacts and forms a thin layer of aluminum oxide on the surface. Nothing can get to it. So it doesn't continue to corrode. All right, we can electroplate spoons with silver. And here's where you get sodium and chlorine out of your reaction. Chlorine gas forms at the anode. Chlorine is negative in sodium chloride, so we strip electrons off of it to make it neutral. That's where the chlorine gas goes. And sodium is a positive ion. We make a metal out of that by adding electrons to it at the cathode. All right, we're done.